Hello and welcome back to Data Science Castnet. You may have seen the buzz around a new method called Gaussian Splatting, which promises high-fidelity representations of real-life scenes that can be rendered much faster than real time. So in this video I thought it would be fun to run over how the method works, why it's different from previous nerve-based approaches, and why I find it so exciting and why everyone else does too. So we'll look at the paper, dive into how the technique actually works, and then I'll explore what the representations that it builds actually look like and what some tricks that we can do with them are. So we could call this general field that this paper fits into something like novel view synthesis or reality capture. The goal really being to describe a scene not just kind of a base 3D structure, but some actual reference of exactly how the scene looks from different views, so that you can render it from different angles. Right, so I have something like this truck here that I found on my walk. The goal is to be able to take this and render it from novel views, and this is incredibly useful for things like virtual production in a kind of movie making or visual effects world where you could capture a background and place an actor in that scene, game development, sharing structures, be it like real estate listings or interesting archaeological discoveries, anything where you want to share a real sort of highly accurate and useful representation of a 3D scene, because the world we live in is in 3D. So for something like VR where you could actually go and enter and inspect a site, that's incredibly useful. And so there's been a few different ways people have approached this. One that's popular historically is something like photogrammetry, where you find matching patterns across different images taken from different angles, and you use that to pinpoint specific actual points, like points in 3D space, and build up some geometry from there, and then you can project some texture onto it. And so this gives you like a 3D mesh, which can be very useful if you're wanting to incorporate this into a game. It's very easy to mix and mash and edit together different meshes that have been captured in different scans, but there's some downsides. So photogrammetry historically hasn't worked at all well for anything shiny or reflective, because there's no patterns for it to latch onto, and also those things look different when you view them from different angles, whereas when you're breaking everything down into a simple mesh with a texture, maybe you don't capture those view-dependent effects. So something that's sprung up to address that more recently is the idea of like a learned representation of the scene, the king there being this idea of a nerf. So you've seen nerfs, and there's a million now nerf derivatives and different takes on that idea, but at the core you're using a neural network, right, something with a bunch of learnable parameters to represent your scene in this learned way. And how nerfs specifically do it is they have a function that basically maps any point in space combined with any viewing angle to an output, usually like an output color and an output density. And so now if you want to render a scene, you start from your camera and you trace through and you evaluate your neural radiance field at every point along some ray. What is the density here? What is the color I should be seeing? And you can use that to render your scene. Now this is great because it gives you like an implicit representation of the scene. There's no geometry, there's no structure, which can be really cool, and it's something that you can learn and optimize, so you just have this representation continuously updated until the renderings from all the original camera angles look good, and then you hope that it still looks good from other camera angles. The downside is this is quite slow, right? It's really slow and finicky to train these models. It's also slow to render because you're having to evaluate this big neural network at every point along every ray. And they don't necessarily do everything perfectly either. There's lots of artifacts and downsides, partly because the model has no concept of the actual structure of the scene, usually. And so it's doing equal amounts of work for all of the transparent air or glass in the scene as it is for any of the solid objects. So there have been attempts to address this by partitioning space and having different learned representations for different parts of the scene, allocating more of the neural network parameters to places that are high detail, but it's still a very tricky balance. So where Gaussian splatting fits into this is it also gives us a learnable representation of the scene, but instead of that being some sort of general parameterization, it's an unstructured kind of like a point cloud. It actually uses these Gaussians, these anisotropic Gaussians, and we'll learn what that means, to capture the underlying geometry. And the great thing about this is that you can have nothing where there's empty space, and you can allocate more of these Gaussians to represent high detail areas, And so we'll see in the paper they're able to update this representation over time and do it all in a very fast and differentiable way so that you can still optimize it. It's still some learnable parameters, but there's no neural network. It's just the parameters of these Gaussians that we're optimizing. And this has a lot of benefits. This gives us something that, thanks to the hard work of the team and some very clever graphics algorithms, is incredibly fast to render, hundreds of frames a second, which puts it in the realm of things that you can run real time, even potentially on something like a portable VR device. So much faster than a lot of existing methods. It also gives a very high fidelity, so they show in the paper they beat a lot of the existing state-of-the-art techniques that are nerf-based. They show a better reconstruction and a higher quality with less artifacts view of a scene, given that as long as you capture it in high detail. So this is a very, very attractive technique. It's also great because it's much easier to mix and match and edit and shift things around again, because you've got this discrete structure that kind of maps to the underlying geometry, as opposed to something like a nerf where editing nerfs has historically been tricky at best. So for the rest of this one, like I said, we're going to go into the paper and see exactly how they implement this magic. We'll also dive into some code and mess around with some scenes that I've captured to see what we can do with them. It's going to get fairly technical, but I'll try and keep it with some fun visuals going in the background, so that if you're a little overwhelmed by the maths, you can always just look at the pretty pictures. And this is not going to be my only video on this topic, I suspect, so if there are things that you would like clarified, or if there's something that you don't understand, do leave a comment down below and I'll try and address that in a future video or in some other sort of, maybe a blog post or something like that. Alright, let's dive into the paper. Alright, so this is the paper that talks about and introduces this method by a group out of INRIA in France and some collaborators from Germany. Very, very impressive work. Now the downside of submitting as a PDF for some journal is that you don't get all of the lovely real-time 3D or video visualizations, so I highly recommend also checking out their website, and all of this will be linked down below. They have a really nice video and some good video sort of before and after comparisons that are a lot nicer than the paper itself in terms of seeing the pros and cons of the different approaches, comparing theirs with various other existing techniques and also with the ground truth. So you can see theirs is not perfect, but compared to any of the other existing methods, very, very impressive. So do go check it out, go watch some of the videos. We're going to dive into the paper, and it is a fairly dense paper, so we're not going to go completely crazy and explain every single equation. Rather, I just wanted to give an overview of the method so that you understand what's going on a little bit more when we come to the code. Okay, so they introduce here, our method, radiance fields are great for novel view synthesis, multiple photos or videos, but it's very tricky to get high quality and they're costly to train and render. And if you do faster methods, you're trading off quality for speed. But they're going to introduce their method, and it has three key elements: competitive training times, high quality real-time novel view synthesis. So yeah, this is going to be their contribution. I think it's a really great paper. And their contributions are, they say, we introduce anisotropic 3D Gaussians as a high-quality unstructured representation of radiance fields. Right, so they're representing a scene with these Gaussians. They also contribute an optimization method to optimize the properties of these Gaussians, and this thing called adaptive density control that gives you these high-quality representations of the scenes. And finally, they're also giving us a fast differentiable rendering approach for the GPU, which is visibility aware, allows anisotropic splatting and fast backpropagation to achieve high-quality novel view synthesis. And the key thing here is fast. If you were to naively try and render a million Gaussians onto some sort of image plane, you could bog things down really quickly, especially trying to trace the gradients back. And so by making this fast, by really spending the time tweaking their kernels and coming up with very clever methods for how to do this, this is kind of what enables the other parts of this paper. Because if you can't render and figure out how to update those Gaussians quickly, then you can't create your scene representation because every iteration might be too slow. So their speed is actually really a key part of this. And as a bonus, you also get fast rendering for inference when you actually want to view a scene. But yeah, this fast differentiable rendering is extremely useful, and very nice of them to have made this all available. Okay, so they go into some background, traditional scene reconstruction, neural methods, radiance fields, point-based rendering. What we are interested in is their actual approach. So, differentiable Gaussian splatting. It's a mouthful. So they want to create this representation. They are defining a Gaussian with a full covariance matrix. At some point, don't worry, I'll explain what some of these terms are. But yeah, this is the key. Let's actually just jump straight to the diagram. So the representation of the scene is with these 3D Gaussians. Here they're showing these little 2D blobs. We'll see later these are effectively the same thing, just arranged in 3D. So they have like location, rotation, scaling, density, color. And the idea is that we can view these from different angles using like a virtual camera. So when we take our input image, we can also project our 3D Gaussians to render them from that same viewpoint in a differentiable way. Then we can compare that with the actual image, the ground truth, and we can find the error and we can trace that error back to say how do we update these Gaussians to improve the rendered image. And we can do this from all the different viewpoints at once, again and again and again, updating each time, slowly getting better and better and better. Now they have some clever insights around what do I start with? Do I just start with random Gaussians scattered around? And they show you can do that. But actually the way that you find the camera poses involves finding these overlapping patterns, tracing those back to 3D points. And so they say, well, if we've already done this process of figuring out where our cameras are by tracking certain points in the scene, we might as well scatter a bunch of Gaussians around those points because that's likely to be where the geometry in the scene is. So that's their clever initialization. And then the final component that makes theirs really effective is this adaptive density control. So let's run through very briefly the different stages that are represented in this diagram. So optimization, they're going to have a opacity that they're optimizing as well as the size and so on. So they've parameterized their Gaussians. And then they're going to have a loss function that they say combines an L1 loss with this DSSIM term, right? And this is not too important, it's just mixing together two different ways of measuring how similar is my rendered image with my actual image, right? So comparing the projection that you've created from your cloud of Gaussians, comparing that to the actual ground truth image from the scan. So they have a blend of different ways of measuring that. Okay, so that's the optimization target, is we're just going to move these Gaussians around and change their parameters until we match our images. Adaptive control of Gaussians, they start with a sparse set of points, and then they have this really neat approach where they're iteratively densifying, that is adding more Gaussians, and then also removing any Gaussians that aren't being used. So you can see here they have a case where we have some complex piece of geometry and the single Gaussian just isn't cutting it, so they can duplicate that and then continue to optimize, and now they can represent that object a lot more accurately. And this is the 2D visualization of something that's actually happening in 3D, but the idea is the same. Likewise, they have something that one single Gaussian is covering a large area, but it's not able to represent it accurately. You would have a high error here. They can split that Gaussian and again continue the optimization process. So this is, in both cases, very similar. They're just finding places where I'm not reconstructing things with sufficient quality. I'm going to add more Gaussians to increase the amount of parameters available to represent that part of the scene. And then you also have this this alpha, this transparency, and they have a culling approach. So anything that is below some certain cutoff threshold, like it's just too transparent, it's probably not needed to represent the scene, right? This might just be Gaussians that were initially in empty space. They're no longer needed, they can be removed, right? And so this balance of we're adding more Gaussians where they're needed, we're removing any that no longer are contributing to the scene. This combination together is going to allow them to gradually add more and more useful geometry, or useful Gaussians rather, right? Build a more and more detailed representation without necessarily hurting the scene by just having, way too many, right? So it's this balance, and I think that's really neat. Okay, and then the fast differentiable rasterization, I don't think we're going to go into now. Yeah, as far as results go, they pretty much trump any of the other available techniques, and all of these are incredible techniques. I mean, if you look at the original NERF paper or papers back a few years ago, the quality of these successes, the instant neural graphics primitives from NVIDIA, Planoxels, MIPNEF, all of these added a lot of extra features to the original idea, or changed it completely and showed much better performance than anything that had come before them. And now we're able to see yet another leap over that in quality. So this is the column that's this method introduced in the paper. This is the actual ground truth rendering of that view. And you can see fewer artifacts in the tires, higher detail in far background scenes. Ideally you would zoom in a lot more and scan this, but yeah, if you go through you'll just see a much higher fidelity in general to the original scene. And if you look at these in motion as well, you'll notice far fewer artifacts, as long as they've been trained well and with high quality input. And so yeah, they compare peak signal to noise ratio, higher is better. They almost match the best. MIPNEF, I believe, also optimized like a special background and has lots of other tricks. Then yeah, it's nice. The reason they have multiple, they show one with 7,000 iterations of training and one with 30. And the reason they do that is to show, look, on training time we can do the quick training, right, which is about comparable to the NGP from NVIDIA, and in that case we're more accurate than those. Or we can do the slightly longer training, which again, this is short. Nerfs used to take 12 hours, 48 hours to to train, so all of these are ridiculously fast and efficient compared to even 2 or 3 years ago. Yeah, we can train for a little bit longer and suddenly we get higher quality and we're beating the best in terms of quality, not just the best in terms of speed. And so they show that trade-off there. The longer you train, the better it is, but it takes longer. And there's a lot of balancing that you can do to say, maybe for a simple scene we only need 10,000 iterations as opposed to 50,000. Yeah, so highly recommend, if you are interested, go into the paper a little bit more detail. But for now, let's stop with this, and instead let's jump over to some code where we're going to actually load in a scene and see what it looks like to interact with this and to try and do some tricks with it. Okay, I think it's demo time. So we're going to look at a scene that I've captured. This was before I'd figured out any best practices, so I just took a bunch of photos with my phone of this little staged scene with different angles. I've since found out that it's probably easier if you take a nice smooth video and then extract frames from that and use more frames than I have here. But this was just the little demo that I had loaded up. So let's restart this notebook and then yeah, just run through what I'm doing, and we'll use this as a chance to look at what is actually going on in this scene representation, and maybe look at also, we can check out the training code if we're interested, but just start to see what we can do with this once we have this representation. So I'm just running some code that is mostly copied and pasted from their rendering, their render.py file, just so that I can specify where my trained model is, my output scan, and where the input images and mapping and so on are. There are GitHub instructions on how to set things up if you want to train your own scans. But this is rendering from one of many views, and we get this image. So actually let's straight away inspect views, and each of these corresponds to one of the cameras in the original scan that I did. And that's not very helpful. It's telling us this is a camera, but it turns out this has some number of parameters, including things like the field of view in the X and Y directions, a rotation and translation matrix to say whereabouts this is positioned and where it's looking. So each of these views encodes some direction and view that maps to one of the original cameras. So I quickly wrote some preview functions to be able to render from a given view. So we can call here render and then pass in one of those views to see this is a camera that was facing from the back. And then also, don't worry about this, but just if you want to preview as a little arc, I got ChatGPT to help with the coding, just adding some small rotation and updating the camera with this new rotation and translation matrix. Anyway, so that's a way to preview what we're doing. So let's take a look at what's actually in the scene. And the main thing that stores the scene's representation is this Gaussian's object. This is the collection, this Gaussian model, a collection of all of these individual blobby Gaussians and isotropic Gaussians that represent our scene. And if we look at this, we see that this has got a number of features. So XYZ, pretty easy to guess. We have roughly 1.3 million Gaussians in this scene. and for each one we have 3 numbers representing the x, y, and z coordinates. So this is like the location in some space. Then we have this features DC and features rest, which I'll talk about now. Scaling, so some can be larger or smaller. Rotation, and this is where we start to get to the anisotropic. This isn't just a sphere, this can be elongated into like a long tube or a rectangle, and then we have a rotation and an opacity. And so for each of these ones, in addition to the color and the position and the size, we have an opacity for how transparent it is. And remember I said during training they remove ones that are mostly transparent, and so yeah, the ones that are left will have some usefulness, and these values will be run through some function when they're actually rendering. Anyway, what about this features DC and features rest? Now I mentioned color, and it's a little bit hard to understand if you're just looking at their source code what's going on here. So what I did to understand this, and this is helpful if you're coming to a new code base, is I took their code. Now I knew sort of what was going on. They'd mentioned spherical harmonics, and if you look that up you'll find lots of quantum physics videos and see how this is like different distributions on a sphere, and it comes up in like electron orbitals and stuff. Don't know how that ties into graphics. So I looked in their function and found where they were loading up, loading up something that had previously been saved, and I found all of these variables being set from, you know, some function. So I just copied and pasted a chunk of this code into let's find it here, into this GPT-4, and I said, hey, you know, here's a bunch of code that I'm looking at. I know it's dealing with some sort of representation of color using spherical harmonics. I want to find out how these are represented. I can access these. Help me, you know, give me some insight. And thankfully it came through. It gives some background, some assumptions as to what these are likely to be, and it correctly identifies that this features DC is the sort of base color, right? If we look at the notebook here, the shape of this features DC, there's 3 values for every Gaussian, right? So this could be like an RGB value, and GPT-4 correctly noticed that and said this is probably the like 0th order component of this spherical harmonic series, and this is probably the rest of the features. Now it deduces correctly that if we have 15 of these plus the 0th order term, then that's 16 that matches a 3rd degree spherical harmonic series. And again, that's a complicated physics term. We're going to dig into this because we actually got some code back to say here's how we inspect it, and then I asked can you visualize that, and got back some visualization code too. So this is very helpful because now we can pull out these coordinates and see, okay, so if we have red, green, and blue, so we're going to have 3 different like spherical harmonic representations for the different colors, and so for each of them we have these different terms, up to 15 terms, and thankfully we can go and evaluate those using, in this case, SciPy, but there's other libraries, or you can find the maths yourself, and this means we can render this. And what this gives is, instead of just having a single color for the Gaussian, it gives it a different color depending on which angle you view it. And so if we now go for a bunch of different angles around 2 different axes, fine, theta, we go and figure out what those angles are, and we calculate the color, then we can pass in a given, we can say, okay, I want to look at the 1000th point, right? So I'll pick a single Gaussian, and then I'm going to calculate out what the color is if we're looking from different angles, and display it on a sphere. And so you can see here this Gaussian is kind of bluish, and it's lighter on one side and darker on the other. If I look at a different one, so I just picked the 100,000th point, we get a slightly different color. Let me just make sure that I've run these cells here. Yeah, so we can go and change this. If we look at the 200,000th one, it's probably a different color. Yeah, it's bluish again. So I thought that was kind of cool to see, okay, this is what this means. If I look at this one from the top left, it's going to look reddish. If I look at it directly from on top, it's going to be silvery. If I look at it from underneath, maybe it's gray. And actually, if you average these coefficients across all of the different Gaussians, you get this kind of map of the lighting, I guess, in the scene. At least that's my thinking, which might be useful later if we want to relight this. Sorry, it takes a little while to run, but yeah, here we have this is like the average of all of those colors, slightly lighter on top, and actually just if we plot this as a color map, you can see, imagine this wrapped around the sphere, lighter on the top, darker on the bottom. So this is pretty useful. This means that you get this view-dependent effect, and if you're looking at something reflective, it can have, you know, a shiny highlight from one direction and look dark from another because it's reflecting some dark object. Okay, so that's our representation. The others like position and scale, those are hopefully more self-explanatory. So in this notebook I wanted to have a little bit of fun, And so what I did was I set up a loss function. Now I'm not going to go into clip or anything here. I've done past videos if you look at the AI art lesson or series, or I can link to a tutorial where I run through a notebook that defines a lot of these loss functions. We can set up, the key here is that we can set up a loss function that looks at an image and compares it with a text prompt. So let's do a text prompt for red and green child's painting. And then we can calculate a loss between our rendered image and this text, right? And this number, the higher it is, the more unlike these two things are. We're going to try and optimize our parameters, in other words, the features of our Gaussians, to bring this loss down and hopefully look more like the text description. And so that's exactly what we're going to do. We can comment out, don't really want to change the location, scaling, opacity. I'm just going to optimize the spherical harmonic coefficients, so the colors and so on. And I'm going to do this by rendering for every view, rendering an image, and then calculating the loss between that rendering and my prompt. And you can add additional loss terms here if you want to also keep it matching the ground truth. But to make this even more dramatic, we're just going to update this and watch as it slowly starts from the base scene. And every time it's doing this, it's calculating the loss, it's finding the gradients. In other words, how do I change the colors of these Gaussians to better match this text description of a red and green child's painting. And so this takes a little while. While that's going, I can preview the previous one I did, which was to start from the scene and slowly optimize towards a Van Gogh painting of a starry night. So you can see here the scene is getting more and more warped and distorted. And if we look at it with that preview function that we wrote earlier, we can see that it's updated these Gaussians to have these kind of swirly textures and patterns. Very low quality GIF, and even the video is rendered pretty low. But it's happening, right? This is changing the scene, and specifically in this case we've only said change the colors to make this look like a red and green scribble. And slowly but surely it's updating it away from the naturalistic scene that we captured towards our description. Now this is very rough and ready. You could do a lot to improve this, tweaking the learning rate, having different learning rates for different features, using a more useful loss, adding in a perceptual loss to match the original scene. The point here that I wanted to make is just that this is even possible. Because, and this is the key, we have this fast differentiable rendering function that the authors of this code created that lets us take these Gaussians, turn that into an image, and then trace gradients back to say, how do I update the original Gaussians to change something based on this image? So I think it's a pretty powerful technique, and there's a lot that you can do with this. And maybe as a demo, I can pull up the viewer here. So this is a scene that I captured just with my phone walking around a car, but I was able to then optimize that based on a different image that I created looking like a kind of stylized game. So you can see it's got these like dark outlines here, this pretty weird texture, and again this view dependent these spherical harmonics mean that when you look at it from different angles you get these different effects, and in this case it's a little glitchy, but it's certainly different to just having a single mesh that only has a specific color at each vertex, right? This is a much more dynamic scene, and I think with a bit more care given to lighting and so on, you could really get something super interesting and stylized. While we're here, it's worth showing, and I apologize that this is small on the screen, these Gaussians, we can change the scale, so we can make them smaller, and you can see each of these dots is one individual Gaussian, right? It has a location, it has a scale, it has a color, and if I change direction, that color might change. So some of them might get darker or brighter to reflect the reflections off the windshield of the sky or something like that. Yeah, so this interactive viewer is a pretty nice way to get an intuition for how, yes, the scene is in fact built up of a number of these Gaussians. Anyway, so I hope you liked that. I will be sharing some more examples on my Twitter, so check that out if you're interested in seeing. I'll probably share some more experiments. This is the original car, what it looked like. So quite a drastic change, but still a lot more that you could do. I was kind of going for a Borderlands aesthetic. Yeah, and you can also do this with using images to define the style. I'm looking forward to seeing people's experiments with relighting. Because each of these ones is just a point in 3D space, you can filter to extract certain objects and do things with them. Yeah, so that's why I'm excited. Hopefully that sheds some light on what's going on under the hood, and why I think it's pretty cool that we have this representation that we can then mess with. Yeah, I'd encourage you to go. The code is, like I said, they've just put it out there. There's no expectations on the authors to have to make tutorials or anything, but I thought it was, yeah, worth taking a look, exploring what's going on. Go and read their training function. It's pretty nice. I think we can find here the actual training. Let's see. So we have def training. We do some setup. We're creating our scene. We have different viewpoints and things. Okay, and then let's go. Every few thousand iterations, we're going to increase the degree for the spherical harmonics until we get to our maximum. So we probably start out with just the base color and then add a little bit of view dependence and then more and more until we have all of those 15 extra coefficients for degree 3. Okay, and so then we're going to render. We're going to calculate a loss, and you can see here this is the loss described in the paper. The L1 loss between the image and the ground truth, that's just like a what is it, mean average error. And then they also have this DSSIM, this additional loss. And then they go loss up backwards, and that's going to go and add a gradient to each of the Gaussian's parameters, which they can then use to update them with an optimizer.step call somewhere. Then you can see the additional steps that they talk about, densification, which is saying if we have one that is worth duplicating, we can add more Gaussians there. Where's the opacity filtering? Densify and prune. Okay, yeah, so this is where they're just adding Gaussians where needed, removing ones if they're transparent. Here's where they're actually doing the update and then resetting the gradients back to 0 and saving checkpoints every so often. So it's really complicated to come to code like this when you've never seen it before. But if you've done any of my past courses and things, you'll know that somewhere in all of this, there's always that same training loop of like setting up the parameters that we're optimizing, right? Somewhere up here, they'll be creating the Gaussians, and then in a loop, calculating a loss. You know, here they're rendering the image and then calculating the loss between the rendered image and the actual image. Lost up backwards, optimizer.step. It's just another optimization loop, but obviously they do it really nicely. They have all sorts of tracking. They have different learning rates for different parameters, all that fancy stuff. But at its core, the whole this whole endeavor is enabled by the fact that we can just call render and pass in our view that we want to render it from, pass in the Gaussians, the actual model, what background to use, and we're going to get back this image that we can then do some deep learning, well, some optimization at least with. Anyway, I'm probably rambling, but I hope you found that useful. Stay around, we'll probably do some follow-ups, but if not, leave comments with questions down below and I'll try and get to them. Thanks for watching.